So in order to understand solution chemistry, that is the chemistry of reactions happening in an aqueous media with water as a solvent, we need to understand first the nature of the solute. And the best way to determine or to distinguish one solute from another will be through electrical conductivity. Whether the solute conducts in water electric current or not. And there's three classifications. We have strong electrolytes, we have weak electrolytes, and also non-electrolytes. Okay, now strong electrolytes, as the term suggests, basically strongly conduct electric current in water. Okay, all strong acids and strong bases are strong electrolytes. Okay, so strong acids and strong bases. At this point, we have not discussed strong acids and strong bases yet, but we will remember this part later. Okay, what else are strong electrolytes? You also have most ionic compounds. Again, most ionic compounds. Okay, I did say most, but not all, because that ionic compound should be soluble in water. Okay, we will be looking at some solubility rules later. So therefore, those which do not dissolve in water at this point, again, only at this point, we will not consider them to be strong electrolytes. But again, it's mostly ionic compounds, such as, for example, sodium hydroxide is an ionic compound which is soluble in water. It also meets the strong base criteria, as we will discuss later. But anyway, in aqueous solution, sodium hydroxide completely breaks up into sodium plus ions and hydroxide ions. Okay, that's what the strong electrolyte means. The compound, whether it's a strong acid, a strong base, or an ionic compound which is soluble, completely breaks up into ions in solution. Okay, once again, strong electrolyte is a compound which completely dissociates or breaks up into ions in solution. We also have strong acids. So for example, H2SO4 sulfuric acid is a polar covalent compound, but it still is a strong acid. Okay, it breaks up into two hydrogen plus ions and a sulfate ion. Okay. Now on the other hand, for weak electrolytes are basically everything in between. Well, strong electrolytes and non-electrolytes. So weak electrolytes, there are weak electrolytes, for example, are weak acids and weak bases. Okay, we will discuss what weak acids and weak bases are again when we go later into acid-base solution chemistry. But basically, these weak electrolytes, unlike sodium hydroxide and sulfuric acid on the left, they partially break up into ions only. And as we will see actually when we go to 106, or when you go to 106, most of these weak acids and weak bases react with water to produce hydronium ions and an ion that is for weak acids. And then for weak bases, they react with water to produce an anion and hydroxide ions. But again, the production of all of these ions are very minimal. Okay, so again here, this one, the concentration of the ionic products are low. Okay, so low concentration of ionic products. Okay, and that's why also too there's an equilibrium arrow here, which just means that both of these reactions actually proceed. But again, however, since these are weak electrolytes, then let's say for example this is formic acid. Okay, formic acid, intact formic acid actually has a higher concentration than hydronium and acetate ions. Okay, the same thing with ammonia. Ammonia has a higher concentration than ammonium and hydroxide ions. Okay, now if you have non-electrolytes, most of these are organic compounds. That being said, formic acid is an ionic compound. So we will not really establish a rule here for distinguishing non-electrolytes and weak electrolytes. But the non-electrolyte, nonetheless, actually does not conduct electricity, meaning they do not undergo this dissociation reactions at all. Okay, they do not dissociate at all in solution, and because there are no ions formed, they do not conduct electricity. Versus for weak electrolytes, at least there are some ions produced. That's why this light bulb here actually only has a dim glow. Okay, so for example of non-electrolytes are sugars, sucrose, glucose, dextrose, etc. Okay, but here's a good flow chart actually telling you what compounds are strong, weak, or non-electrolytes. So again, as you can see here, most ionic compounds are strong electrolytes. Okay, for acids and bases, or for covalent compounds, strong acids and strong bases, okay, actually strong bases too, or strong electrolytes as well. Now weak acids and weak bases will be weak electrolytes, and then again most molecular compounds with some overlap again here with weak electrolytes are non-electrolytes in nature. Okay, we're gonna go over this example in class and this one as well, but I want to go over this problem when we are actually calculating for the concentration of electrolytes in solution. Okay, so for this problem you are asked which of the following solutions of strong electrolyte contains the largest number of ions. In some problems you will have to actually just know the concentration of one of the ions of a strong electrolyte. And in order to do that, let's look at these examples. So let's say for example sodium hydroxide. Okay, sodium hydroxide, remember, has this formula, NaOH. Okay, and again as we have discussed before, for sodium hydroxide you have 1 mole of sodium for every mole of sodium hydroxide. Okay, you also have 1 mole of oxygen for every mole of sodium hydroxide, and you also have 1 mole of hydrogen for every 1 mole of sodium hydroxide. Okay, now we can say the same relationships too with ions. Remember that sodium hydroxide is from sodium plus and hydroxide ions. Okay, so if we actually rewrite this, we can also write that for every 1 mole of sodium hydroxide we have 1 mole of sodium plus ions, and also for every 1 mole of sodium hydroxide we have 1 mole of hydroxide ions. Okay, so for this one actually if we're just looking at concentration, we can actually say that if you have 0.100 molar of sodium hydroxide, okay, then that actually also means you have 0.100 molar of sodium plus ions and 0.100 molar of chlorine ions. Okay, now if this was, of course, for example, something like barium hydroxide, then it would have been a 2 to 1 ratio. You have 1 mole of barium for every 2 moles of you have 1 mole of barium for every 1 mole of barium hydroxide, and you have 2 moles of hydroxide for every 1 mole of barium hydroxide. So here again, if this was just given, we'll work on this one actually anyway. This one would have been 0.100 moles of barium 2 plus, and then this one should be 0.200 moles, or molar rather, of hydroxide ions. Okay, but let's focus first again at the first problem, because we're gonna work on that problem anyway next. I guess I'm just getting ahead of myself. So for this one, this relationship will apply to molarity, but it will also apply to moles. So to solve this problem, I want to first calculate how much moles of sodium hydroxide I have, Okay, because here you're asked anyway which just has the largest number of ions. I mean, didn't ask you whether it's number of ions as in Avogadro's number, as in using Avogadro's number, or molarity. It just asks us for which one has the largest. So let's just compare them by moles. Okay, the number of moles of sodium hydroxide, okay, or to calculate for the total ions in sodium hydroxide. So that will just be, let's take first this molarity and volume, okay. If we actually, well, let's first convert 100 ml into liters, okay. Again, remember that for aqueous solutions, N is equal to mv, okay. So here, 100 and then 0.100. We can re-express their molarity as moles per liter, okay. Liter cancels out, and this term actually gives you the number of moles of sodium hydroxide, okay. Now again, for every 1 mole of sodium hydroxide, we actually have a total of 2 moles of ions, okay. So this one should just give you 0.20, or sorry, rather 0.0200 moles of ions in sodium hydroxide, okay. And then we can do the same thing too. Let me just add one more slide. We can do the same thing too for barium chloride, which is the next problem. So for barium chloride, you're given here that you have a concentration of 0.200 molar, and the volume is 50, okay. But again, remember that barium, oops, sorry about that. But remember that barium chloride, okay, as a strong electrolyte, breaks up into barium 2 plus and 2 Cl minus ions, okay. So here you actually have a total of 3 ions, which by the way is just the sum of these subscripts. Now be careful with polyatomic ions, of course, when counting these subscripts. Okay, so that's a total of 3 ions. Again, the number of total ions, or number of moles of total ions, should just be 0.0500 liters times the molarity 0.200 moles per liter. Again, this term gives you the number of moles of barium chloride, okay. And then to cancel out moles, we just write here 1 mole of barium chloride, and again that's 3 moles total ions in the formula, and this one should just give you 0.030 moles of ions in barium chloride. And then lastly, we have sodium phosphate, okay, and this one we now have a polyatomic ion, okay. So here sodium phosphate breaks up into sodium plus the phosphate ion, okay. But keep in mind that there's 3 sodiums just to balance this equation, okay. We still need to balance that equation anyway. Alright, so keep in mind that again there are a total of 4 ions. Now when you count the number of ions based on the formula, so this one will be 3, and then this entire thing will be 1, because that entire thing is your anion, unlike barium chloride, in which you just have a monatomic anion, okay. But to do the math, it's the same thing basically. So number of total ions will just be equal to 75 milliliters, okay. And then that will be times 0.150 moles of sodium phosphate, okay. So that's moles per liter, okay. Again, this is moles of sodium phosphate, okay. And then that will be times the stoichiometric factor or dimensional analysis factor will be for every 1 mole of sodium phosphate, you have a total of 4 ions. Okay, and this should just give you 0.0450 moles of ions. Okay, this number of course is much larger than this number for barium chloride. And let's check sodium hydroxide. That's actually 0.020. So therefore here, the one with the greatest number of ions should be sodium phosphate. Okay, so that should be sodium phosphate.